cosine x plus j sine x, because that is the Taylor series for cosine, and that is the Taylor series for sine. It has to be true. Everything is going to work together and hang together and be a coherent mathematical formulation. So, and said another way, he showed that r e to the j theta has to be r cosine theta times plus j r sine theta. Well, that should be very, strike a familiar note, because this looks like polar form. Remember, this is a plus jb. That sure looks like a polar form. And sure enough, if we go back to geometry, that's exactly what it is. So here's our representation of a point in the plane using the regular ordered pair notation. But you can also think about a point in the plane in polar form. So there is a distance from the origin. The point is some distance from the origin, and it's some angle. Well, we know how to convert between the two. We know that the a component, the x component, is r cosine theta, and that the vertical component, the y component, the imaginary component here, is r sine theta. So that's where the rule I derived on the previous slide is all consistent with. It's all consistent with this geometric picture of representing something in Cartesian coordinates or polar form. It turns out to hop between the two. Euler's formula had better be true, or else something is very, very wrong. So you know from your geometry that you find the radius just by using the Pythagorean theorem, and the angle is just the arctangent of the ratio of the y and x components. Okay, so we now have two ways of representing the same complex number. One is Cartesian form, a plus jb. One is polar form, r e to the j theta. And these rules are how you go from one to another. Go from polar form back to Cartesian using these rules. Go from Cartesian form to polar form using these rules. And we're going to do that a lot. It turns out certain calculations are better done in one form than another, and you need to be able to go back and forth. And these are the rules that they come from, but these aren't just arbitrary rules. They have to do with the geometry of the 2D plane. Okay, well now this might help explain how some of these weird, if you will, the multiplication and reciprocal rules come from. Well, let's check the multiplication rule when things are written in polar form. So we have two polar form complex numbers, and a little bit of rearrangement just gives us this. And note that you multiply two exponentials together, their exponents add. So that's where this comes from. Okay, well, this is just a special polar form. I'm going to convert it to Cartesian form using our rules. Okay, that's where that comes from. And now I'm going to use the cosine of a sum of angles and the sine of a sum of angles formulas that you learn in trigonometry. So that's where this is. This term corresponds to the cosine of a sum of angles, and this term comes from the sine of a sum of angles, and we're using the j to keep us straight about which one goes where. And I've rearranged things a little bit to put the r1 with theta 1 and the r2 with the theta 2. Well, identifying terms, that is just a1, that's just a2, etc. And sure enough, we come up with the same multiplication rule that we derived for Cartesian form. So that works fine. Now the reciprocal rule can be derived rather easily. So writing z in polar form, that's going to be that. Well, the reciprocal of this is 1 over r times e to the minus j theta, because e to the x, and you take the reciprocal of that, well, that's e to the minus x. So that this has to be true. Well, now convert that to Cartesian form. So e to the j theta is just cosine of theta. I'm sorry, cosine of minus theta is cosine of theta. That's where that comes from. The sine of minus theta is minus the sine of theta, and that's where this comes from. So that's really quite nice. And now you see where this comes from, because if I multiply top and bottom of this expression by r, we see that r cosine theta, well, that's a, and r sine theta is b, and r squared is just a squared plus b squared. So that's where that reciprocal rule comes from. It's most easily derived in polar form, and now everything hangs together. We now understand all the algebra that there is. Now there's one special thing that comes up in complex numbers, which is a new thing, and that's the complex conjugate. It's a very easy operation, but it's not algebraic. So the complex conjugate of z, which we denote by z star, what it does is it flips the sign of the imaginary part. So z is equal to a plus jb, and z conjugate is a minus jb in Cartesian form. And in polar form, what that does is it changes the sign of the angle, flips it. And that's what the conjugate is. And the conjugate, it turns out, is mathematically important for the following reason. You can now use, say, that z times z conjugate is equal to the radius squared. So you have z times z conjugate, well, that's just r squared. So you can derive, if you will, a formula for r just from looking at z. And also, we can define what's called the magnitude of a complex number is equal to r. So another word for the radius is called the magnitude, and the magnitude squared is just r squared, is z times z conjugate. It's this formula that's going to be very, very important for us in talking about complex numbers mathematically. You can also express the real part and imaginary parts of a complex number using the complex conjugate. So the real part of z, which we'll denote by this, the x component, if you will, is equal to z plus z conjugate. So that's a pretty easy thing to see. So you have a plus jb. You're going to add to that a minus jb. Well, when you do that, these parts cancel, and you're left with 2 times a, so you get to divide by 2. And a similar thing happens when you subtract. Now what happens is that the real parts cancel, and you're left with the 2 imaginary parts adding, and you have to divide by 2j to get back to b. So this equals a, and this equals b. So now we can derive the Cartesian components just by referring to the original complex number by simply saying real part, and the imaginary part by saying imaginary part, and get them by using this formula. That's going to be very useful for us in doing some operations on complex numbers. So, how do you use all this to do calculations? Well, what I tend to do is add and subtract in Cartesian form, and I multiply and divide in either form. It depends on the details of what I do. I tend to use polar form, especially for division, and you'll see that in a second. And then I convert between polar and Cartesian forms, depending on what's going to be needed. So here's a little example. Suppose you want to divide these 2 complex numbers. The easiest way to see this, I could use the reciprocal formula, but the easier thing to do is to notice you can play a little mathematical trick. So a plus jb divided by c plus jd. I can multiply top and bottom by the conjugate of the denominator. writing B. I don't know why. That's a D. Okay, I'm multiplying by 1. I'm writing 1 in a fancy way. Well, the denominator is the magnitude squared of that complex number, and then I just have to multiply the two top things together. Well, you can see where it comes from, because 5 is 1 squared plus 2 squared. And there's the conjugate part. And I just multiply them together, and when the smoke clears, you get 3 minus j. So that's a easy way to do a division, in this case in Cartesian form. If it's in polar form, if these original numbers were in polar form, I would have stayed in polar form and just done it that way, because it's very, very easy. Now, another thing that comes up is the magnitude of a ratio. What I want to point out is that the magnitude of a ratio is equal to the ratio of the magnitudes. And I think this is pretty easy to see. If you think about this in polar form, you can derive this yourself. So the magnitude of the numerator is square root of 1 squared plus 1 squared, so you get the 2, square root of 2. And as we've already seen, the square root of 1 squared plus 2 squared is the square root of 5. And so the magnitude of this number is the square root of 2 over 5. And if you find the magnitude of this number, which I ask you to do, I think you'll get the square root of 2 over 5. At least do better. All right. So complex numbers, turns out, are going to simplify our calculations immensely. I cannot stress that enough. It is extremely important for signal and system theory and electrical engineering. Why that is not obvious yet. Just stay tuned and we'll get to it very, very quickly.